Welcome back. This explainer, proudly brought to you by Forge College, is called Implementing ERC-3643 Behaviors on Solana. If you've been following our journey from EVM to SVM, you know we just finished mapping out the theoretical blueprints. Now? Well, now it's time to actually build the thing. We're taking those strict, heavy Ethereum compliance rules and wiring them directly into the lightning-fast Solana ecosystem. Let's get to it.
Here's our mechanical assembly manual for today. We'll start by moving from blueprints to code, design the architecture, build a program-owned mint authority, set up guarded transfers and allow lists, test our shiny new prototype, and wrap up with key takeaways.
All right, Section 1, from blueprints to code.
So, what exactly are we building here? We need to translate three fundamental real-world concepts right into our Rust and TypeScript code. First up, controlled issuance. We absolutely have to keep a tight lid on token minting. We can't just leave the money printer running in the Wild West, right? Second, transfer controls. We need strict rules dictating exactly how and to whom tokens can be sent. And third, permissioned roles. We've got to make absolutely sure the operators pulling the levers actually have the authority to do so.
Moving on to Section 2, designing the architecture. Let's look at the parts list for this build.
If you look at this schematic, you'll see how we translate EVM concepts directly into our Solana parts. Over on Ethereum, you have a centralized issuer. On Solana, that becomes a program-controlled PDA. What about that massive, clunky transfer allow list registry? Well, we break that down into individual PDAs for every single recipient, and those operator roles get their very own separate PDAs too. By taking this giant monolithic EVM state and breaking it into individual Solana accounts, we're unlocking massive parallel processing, all while keeping our compliance completely airtight. It's kind of brilliant.
Now, I'm going to be saying PDA a whole lot today, so let's make sure we're on the same page. A program-derived address is basically a custom security vault. But here's the kicker. There is no private key. None. No human can ever sign for it. It's an address controlled 100% by the mathematical logic of our anchor program. So if the program says no, that vault stays firmly shut. It guarantees that our compliance rules just literally cannot be bypassed by some rogue operator.
Okay, Section 3, program-owned mint authority. Let's assemble the engine.
In a typical token launch, some developer's personal wallet might hold the mint authority. Yeah, we're not doing that here. Instead of a single, fallible human holding the keys, which honestly is a massive relief, our custom Solana program claims the mint authority using a PDA. Token issuance is strictly governed by code now. If somebody wants to mint new security tokens, they have to convince the program logic they meet all the regulatory requirements first. No exceptions.
Which brings us to Section 4, guarded transfers and allow lists. Let's install some checkpoints.
Think of a guarded transfer as the strictest nightclub bouncer on the entire blockchain. Normally, users just interact directly with the SPL Token Program to move their funds around. But with a guarded transfer, no way. They aren't allowed to do that. They have to ask our custom program first. Our program acts as a strict toll booth. It demands that every single movement pass an allow list check before it executes a cross-program invocation, or CPI, to the main SPL Token Program.
So, picture this toll booth. If you try to send tokens to an unlisted recipient, meaning somebody without an authorized PDA, they are going to hit an absolute brick wall. The transaction gets rejected instantly. But if their PDA is firmly registered on the allow list, well, then the program nods, the mechanical gears turn, the CPI executes, and the tokens flow seamlessly to their destination.
Time for Section 5, testing your Solana prototype. Let's put on our safety goggles. To fire up this prototype, we're going to follow 3 exact steps. First up, we compile our Rust code and deploy the anchor program straight to Solana's devnet. Second, we write a TypeScript demo script using the anchor client. And finally, step 3, we execute that script to watch our custom compliance machine run live on the network. Let's see what happens when we hit enter.
When this script runs its very first transfer attempt, your console log should actually spit out this beautiful intentional failure. Allow list check failed. Now, I know normally as developers we despise errors, but actually scratch that, this is exactly what we want. This error proves our guard gate is wide awake and actively blocking unauthorized recipients. The bouncer is doing his job.
Okay, so how do we actually get past the gate? Well, next, our script flips a switch. We execute the allow recipient instruction, which initializes the recipient's PDA and adds it directly into the on-chain allow list registry. With that registry successfully updated, we immediately tell our script to retry that exact same transfer.
And boom,
The terminal prints success. Permitted transfer completed. This is incredibly powerful to see in action, guys. It confirms that our custom anchor program actually verified the recipient's PDA, approved the logic, and then successfully initiated a cross-program invocation to the native SPL Token Program to actually move the funds. We quite literally just executed an ERC-3643 compliant transfer on Solana.
But hey, as engineers, we never just blindly trust the terminal output, right? To verify our machine isn't just pretending to work. We need to inspect the devnet transaction logs. We check that the script terminated cleanly, without any random Rust panics. We confirm the CPI calls actually happened on the Explorer. And most importantly, we verify that the sender and recipient token account balances actually changed. Trust, but verify on-chain.
Now we have one final diagnostic test. We've proven we can mint, and we've proven we can transfer. But what about revocation? We really have to ask ourselves, can we actually shut this minting engine down in an emergency?
The answer is yes. And honestly, it's elegantly simple. By toggling a simple Boolean flag called minting enabled in the program's global state over to false, our program's logic acts as an emergency brake. Any future mint attempts will hit that false flag and be safely rejected. This proves we have total programmatic lifecycle control over token issuance.
Finally, Section 6, Key Takeaways and Next Steps. Let's power down the workshop and review.
If you take away absolutely nothing else from this explainer, please remember these golden rules of Solana virtual machine engineering. First, program-owned authorities give you centralized, unbreakable control. Second, PDAs are absolutely the best way to handle complex segmented state for things like allow lists. And third, CPIs are how you safely complete the actual accounting after your custom policy checks have passed. Think of this as the holy trinity of compliance on Solana. And before you close your IDE today, be absolutely sure to save your blueprints. Specifically, save your deployed Anchor Program ID and your TypeScript testing artifacts. Keep them handy in your repository, because I promise you will absolutely need them to build the final capstone project for this course. As you prepare for that next major step, I want you to ponder this. Today, we explored a pretty simple allow list gate. But how might you upgrade this machinery to require multiple operator signatures before a transfer is approved? How would you build a multi-sig compliance gate using these exact same PDA and CPI mechanics? Think about it, because that is where the real power of programmable compliance lies. This explainer was proudly made by Forge College. I really hope you found exploring these blueprints as fascinating as I did. I highly encourage you to head over to forge.college to dive deeper into this subject and continue mastering the incredible, ever-evolving world of Web3 engineering. Until next time, keep building and stay curious.